Aabhas Gulati from Paul Sabatier University.
Hello. Sorry.
Yes. And then he'll be giving a talk on symmetric states and PPT entanglement.
So yeah, I want to thank the organizers for organizing such a wonderful conference. And yeah, I think you guys might be a little bored of hearing about quantum trajectories. So I might switch some topics here and we'll talk about symmetric states and PPT entanglement. Where's the, yeah. So this is based on the work with Ion Nikita and Cedric Singh. I am a PhD student in Institute of Mathematics at Toulouse, and Cedric is at Cambridge. Yeah, so here's a brief outline of my talk. So I'll spend a few minutes talking about mixed state entanglement and why PPT entanglement is very important to entanglement theorists. And then I move on to symmetric states, and I talk about a class of symmetric states which we call local cyclic sign invariant states, which we introduce in the paper. So mixed state entanglement. So everyone, I think, here knows about pure state entanglement. So quantum states quantum states are described by kets with norm 1, and the separable matrices are just kets which are in a product form, and any vector not of this form is entangled. But in mixed states, we extend this notion to density matrices, which are positive semi-definite matrices with trace 1, and the separable matrices are sort of a convexification of this set. You have a mixture of product states. So Pi here is a probability distribution, and then the Pi is sum to 1. And any entangled state is a state which is not separable. And some intuition about why this is the separable matrices. These are all the states which can be prepared starting from a product state and then and using just local transformations and possibly classical communication. So how to detect entangled states? So in general, determining whether a state is entangled or separable is an NP-hard problem, and there exists possibly no computable criteria, efficiently computable criteria. There is one criteria which is pretty useful, which is called the PPT criteria, which is we just take the partial transpose and check the positivity of the matrix. And if it's not positive, then rho is entangled. And this criteria completely characterizes entanglement for small systems, which is 2 cross 2 and 2 cross 3, but it fails in higher dimensions. And some entangled states also satisfy this criteria, and they are called PPT entangled states. So PPT entanglement, the physics, why is it important? So these states which are PPT entangled, they exhibit some unique physical properties. First of all, they provide no advantage for tasks like quantum teleportation, and you cannot distill any entanglement out of these states using LOCC. These first two things are like separable states. They behave just like separable states. But the third thing, they have a non-zero entanglement cost. That means, unlike separable states, you need some entanglement to prepare them. And they also sometimes provide advantage in tasks when they are used alongside non-PPT entangled states. And many open questions are related to these states, PPT square conjecture, and so on. This is a recent article by Barbara Terhal, who was there in the conference and in Physics Today, and they call these states as black holes of quantum information. Basically, you need some entanglement to prepare them, but you cannot distill any entanglement out of them. And it's a very nice article, and you can have a look. So how to detect or construct these states? So the realignment criteria, which was presented by Ion in his lectures, can detect some of the PPT entangled states, which is just taking the realignment and checking the norm. But we need a framework to systematically identify these states. So we look at symmetric states. Symmetries are also physically interesting, and they lead to a reduction in the number of parameters, provide better tests for entanglement. So locally symmetric states, a bipartite state is, I'll call it locally symmetric if its satisfies the following covariant condition, which is U tensor U and U. Yeah, so this is the covariant condition, and then you can also have the conjugate condition, and this is for a subgroup of the unitary group. And if you look at the full group, the full unitary group, you get the well-known Werner states, or in the conjugate case, you get the isotropic states. And it was proved long ago that for Werner states, there is no PPT entanglement. So Werner states there's two classes of Werner states, which are separable and non-PPT, and which are entangled. So they are not rich in the PPT entanglement case. So what we do is we introduce a new class of quantum states, which we call local cyclic sign invariant states. So the covariance condition is just given by these two groups, where we take orthogonal matrices which are diagonal. So they all only have plus and minus 1 on the diagonal. And we take the cyclic group, and for all basis elements, you basically permute the element by this number q, and then the state is locally invariant under the cyclic permutations. And these states are now parametrized by 3 vectors, and such that the first element of each vector is the same. And because there are 3 vectors, you get 3D minus 2 parameters. And so it's a linear scaling of parameters as compared to d to the power 4 scaling in the general case. And this is the explicit parameterization, which looks complicated, but I just want to point out that all the important criteria like positivity, the density matrix being positive, it can be seen as simple conditions on these vectors in the parameterization. So A is non-negative, and the Fourier transform, which is the discrete Fourier transform of B, is non-negative, and there's a simple entry-wise non-negative condition on A and C. Similarly, you can impose the normalization using this parameterization, and the PPT condition also you can write in terms of the discrete Fourier transforms, and rho ABC is a separable state if and only if A, B, and C satisfy this complicated looking convolution. This is the convolution, and this is the entry-wise product of vectors. So it satisfies with some VKs and WKs this complicated looking equalities, and this makes the deciding separability still a non-trivial problem, but it makes it easy to construct and detect PPT entangled states. So there's a simple construction of PPT entangled states in this class, where we take the B to be a vector where we have 1 omega square, where omega is the dth root. And in such a case, selecting C optimally using this Fourier transform, and we get a simple condition on PPT where AI AD minus I is greater than or equal to 1, and the state is separable if and only if AI is greater than or equal to 1 for all I. And so it's easy to see how to construct a PPT entangled state using these two conditions by choosing A1 to be 1 by mu and AD minus 1 to be mu not equal to 1, and selecting AK. And this has an easy construction of PPT entangled states. Finally, we also can impose some interesting symmetry, which is we apply a swap operation on the state rho, and still it's equal to the state. And in this case, we reduce the number of parameters further. And in this case, A is equal to C, and B is now proportional to this vector, which is 1, 0, 0. And the parameterized state now is just given, it's diagonal in this basis. This is called the dk basis, and this dik is just I plus k, and there's a proportionality factor. And these parameterized states, now you only have one vector which parameterizes them, so it's easy to look at the geometry. So now rho A is PPT if and only if A is entry-wise non-negative and the Fourier transform is also entry-wise non-negative. And you see that these are two linear conditions. So this is now a polytope. The PPT cone becomes a polytope, and rho A is separable if and only if A is has this convolution. This is the autocorrelation function of this VK, and you have a convex mixture of autocorrelations. And it's known that rho A is PPT if and only if rho A is separable, if the dimension is less than or equal to 4. So the first non-trivial case is dimension 5, and actually these conditions also imposes some reduction on the parameters, where now the system can be described by this d/2 floor plus 1 parameters. And for d equals to 5, we have 3 parameters, and we can normalize the first parameter. And what we get is a very interesting geometry where you have the PPT cone in red. You can see it's a polytope. And you get this in blue, you have separable states. This is in dimension 5, and you see the PPT, this is the separable part, and there's a slight curve and it joins the PPT cone. So there in this region, both these regions, you have PPT entangled states. This is the full characterization of the geometry in d equals to 5. And we can have some partial results in d equals to 7. And on the facets, you have this is the separable thing in separable states on the facets of this thing. And you have the PPT cone, the polytope, PPT polytope, and you see there's PPT entangled states on the facets. But the bulk of the geometry is still open. We don't know what it looks like, but still you can see some PPT entangled states on the facets. So this is a final overview of the symmetric states which are analyzed in the literature. So if you have the full group of unitary matrices, you get this Werner isotropic states, and the dimensions it's like a two parameter family, and there doesn't exist PPT entanglement. If you extend this group to all the orthogonal matrices, you get the states, Brouwer states, and you still don't have PPT entanglement. And till this point, you don't have PPT entanglement, where you take the diagonal orthogonal matrices and you instead of the cyclic group, you have the full symmetric group in those basis elements. And here are our class of states, and sort of these are the smallest class of states which have PPT entanglement. And it's an important question to see if we can have something in between which has a rich structure of PPT entanglement. So for conclusions, we have introduced another class of states which have 3D minus 2 parameters. The separability problem is still non-trivial. The PPT is not equivalent to SEP. And there are some systematic constructions of PPT entangled states. And we have new results for mixtures of decay states in small dimensions. These states can act as a test bed for important conjectures surrounding PPT entangled states. Question, which is what minimal symmetry that leads to this collapse of PPT and SEP. As we saw before, we know that this is the minimal symmetry, which still there's no PPT entanglement. So the question is, where exactly is PPT entanglement? And thank you. And if you have any questions.
We have some time for questions. Yeah, so I think I have a quick question. Maybe you show us like a picture of a black hole at some point. And then I kind of wonder like what's the connection here? So
the connection is basically like a black hole sucks things and you cannot take things out of a black hole. That's the
So
intuition.
the PPT.
So the PPT entangled states, you need entanglement to prepare those states, but you cannot distill any entanglement out of those states using LOCC operations, the local operations and classical communication. But you cannot prepare those states without using entanglement. You need to give in some entanglement, but you cannot get out some entanglement.
Okay,
so this is why they are also very interesting to study.
Okay. Any other questions? Yeah. Okay. So if not, thank the speaker again, and then so we'll see you tomorrow.